This question is about the reaction scheme shown, and we can see we've got methylbenzene at the beginning, and in step 1 we're nitrating it, and in step 2 we're turning the nitro group into an amine group, and in step 3 the amine group is becoming an amide. If we were to draw that part of the structure out, we've got an N with a H joined to a C with a double bond O and a CH3, so that's an amide. The bottom part, the methyl group is being chlorinated and then turned into a different amine. So what do we need for step 1? Well, step 1 is a reaction onto the benzene ring, so we need to generate this electrophile in order to be able to substitute it onto the benzene ring. So what we would need for that is we need a source of that NO2+, and that's coming from concentrated nitric acid. We need a catalyst to generate that electrophile. So that would be concentrated sulfuric acid. So those two are both needed in step 1. And then in step 2, how do we reduce an aromatic nitro into an amine? That is tin and concentrated HCl. Give the name of the mechanism for step 3. So step 3 is when an amine reacts to form an amide. Now this is the group that we're trying to put on, and to do that we would need to use something that has this in it, and so we're going to use an acyl chloride, and that mechanism is going to be nucleophilic attack by the amine on the acyl chloride, and we're going to add it and then eliminate HCl, so nucleophilic addition elimination. Name the reagent for step 4. So we just go back and have a look at step 4. What we're doing here is replacing a hydrogen with a Cl. So we're substituting a H for a Cl. So it's a substitution, but in order to do that on what is essentially an alkane, the methyl group is an alkyl group, then we're going to need to do free radical substitution. So our reagent is chlorine and our condition is UV light. Then it says amine A is formed in a 2-step synthesis, and amine in step 2, and amine B is formed in step 5. So we can have a look at those there. And then it says explain why the yield of B in step 5 is less than the yield of A in step 2. So when we're forming amine B here in step 5, we're doing nucleophilic substitution. If we aren't careful with our conditions, if we don't control our conditions, this amine is able to act as a nucleophile as well, and we're going to get further substitution. Whereas when we reduce a nitro in step 2, we're only going to get one product because there's only one possible product there. So in step 5, there are further substitution products possible, like the secondary and tertiary amines. So it can keep reacting with the halogenoalkane and doing further substitution to give secondary amines, tertiary amines and quaternary ammonium salts, depending on how well you control the conditions. In step 5, there is only one product possible from reduction. Then it says explain why amine B is stronger than amine A. So if we just remind ourselves of the structure, A had the methyl group at the top and the amine at the bottom, whereas B had the amine attached to the alkyl group at the top. So in B, the lone pair on nitrogen is going to become delocalized into, if we think about this sort of sideways on, the lone pair on the nitrogen is going to become part of this pi bonding ring formed by overlap of p orbitals, at making it less available to accept a proton, whereas in B, the positive inductive effect of the alkyl group is going to increase the electron density on the nitrogen and making it more able to accept a proton. So in B, the alkyl group has a positive inductive effect increasing electron density on nitrogen, making it more available to accept H+. If I was going to do that from the other point of view, in A, the lone pair on nitrogen, and I probably should have said in that top one, making the lone pair on nitrogen rather than just it, more available to accept a proton. In A, the lone pair on nitrogen is delocalized into the pi ring, making the lone pair less able to accept H+. So for one of these two explanations is probably fine. You wouldn't have to write both.